So before we go into Ampere's law, the first thing we want to do is define something called current density. So we're going to start off with a discussion of current and then move on to something called volume current density J. So let's start off with current. You probably know this already, but when charges are moving, within a conductor, we can define the current IT as follows. So we have the current being equal to some sort of change in charge over dt, or a change in time. So this is going to be in units of charge over time. That's probably going to be coulomb over second, which we call A, or amperes, or amps. So we should probably define what dq is. dq, as a function of t, is the charge passing through a small part ds, a small part of the surface area ds at a given time t. So then how do we define current? The current is a measure of the rate at which charges are crossing a surface S. So we're going to take a look more closely at this. We're going to first ask us a question. But what if the charges are moving through some volume? So this is a very important question because now we're not really just looking at current. We need to figure out how much current is crossing over a specific volume. So we define something called a volume, not charge density, volume current density. We call that J, and that's a vector. And we're going to define this at some point. So what do? We construct a small area ds relative to the current flow. If we're having trouble visualizing this, we should probably draw a diagram. So the whole idea is that there are charges moving through some volume, and let's just assume we're looking at charges going through some wire. So we can model the wire as some cylindrical tube, and that's our wire. We know that there's going to be some volume current density, so we label this in green. Let's call this J. So we've defined a volume current density J at a point. The next thing, we construct a small area ds relative to the current flow. So first, I can have my ds being exactly perfectly perpendicular to the flow of current, or my ds can be not exactly perpendicular, but somewhat slanted. So we can call this ds. So that's just like a part of a curved surface. So then we consider a current di passing through the surface S. So within this cylindrical tube that we've drawn, we know that there's current flowing through it, or moving charges going through it, and we know that the current is going to pass through some arbitrary surface that we draw. So there are essentially two cases we have to look at. Case number one, we look at what happens when ds is exactly perpendicular to the current flow. So if ds is exactly perpendicular to the current flow, then that means the magnitude of the volume current density at a point is going to be equal to the amount of current that passes through some sort of surface area. So that means this is going to be in units of amps per meter squared. So this would be for some current flowing through some surface. We also want to note that J is a vector, and we have to determine its direction by inspection. So J is going to be in the direction identical to that of current flow. So we can probably assume what case number two is. There's basically two cases. Your ds is perpendicular to the current flow, or your ds is not perpendicular to the current flow. So case number two, we have to look at what happens when we choose an arbitrary surface like the one we've drawn here. And we have to assume that that surface might not be exactly perpendicular to the current. So this is not perpendicular to current flow. So then if the current di flows through an arbitrary surface, then the current through ds is going to be given by di is equal to j dotted with ds, which gives us the current passing through ds exactly along it. So therefore, we can calculate the total current, and that's going to be I is equal to the integral, or surface integral, of j dotted with ds. So we're simply just integrating di. So we've covered what happens when charges are moving through some volume. But when charges are moving, they also have some speed. So we have to ask ourselves another question. What if the charges have a uniform velocity? So let's say that the charges are moving at something called a steady drift velocity u. So how do we try and analyze this now? We've already discovered an equation for di and therefore I. So we've also looked at the volume current density, which tells us how much current is within a volume at a specific point. Now we want to figure out how to incorporate the speed of those charges. So what we want to do is construct a volume like this. So I'll first explain what we're doing. We construct a solid rectangular volume. And how do we figure out this volume? So we take a look here. This is some distance d that the charges are moving. So let's assume that there's also charges inside this volume that are moving this way at some speed u. So if we're looking at how far the charges are moving, we know that the velocity is equal to distance over time, which means distance is equal to velocity times time. So it makes sense that d, or this dimension here, is equal to u dt, or v dt. So that particular change in distance, or the path traveled, is going to be your velocity of those charges times the time it took for them to travel from one end to the other. So therefore, when we take a look at this, we know that the solid rectangular volume is going to have units of, or not units of, dimensions of u dt. And what is this called? So we have the length. What about this? This entire thing is ds. So we're only taking a small differential volume element. So all the charges are going to pass through a surface area on the right. So therefore we multiply by ds to get the volume. So now we construct a solid rectangular volume of dimensions u dt times ds. Let's make sure u is a vector, with ds perpendicular to current flow. So through time, through some change in time dt, all charges within the box will pass through ds. But now this raises another question. How many charges are there? I drew 3 charges, so let's just assume there are n charges. So if there are n charges, and we should probably give them a name too. The charges can each hold a value of charge q. So if there are n charges per unit volume, each of charge q, then the current can be redefined as follows. So we already know we started with di being equal to dq over t over dt. So I'm talking about di now, which is just a small change or differential current element. So I have n number of q charges multiplied by ds u dt, which is the volume element, over dt. And that's equal to nq ds u. So just looking at this, it looks like I'm multiplying some sort of density times a volume element over some sort of time. So it makes sense that our NQ would be considered some sort of volume current density. So then this means, the volume current density is going to be J equals, we have di over ds, as we discussed before. That's going to be basically nq dsu divided by ds, so we can take away the ds and get nqu. Okay. So the other thing we want to do is take a look at this equation. We know that the volume current density is equal to nqu, but we can let rho v be equal to nq for some sort of current density. So we simplify. J is equal to nqu or rho v u. So we've gone through volume current density J. We were able to define it as di over ds, and we were also able to figure out the total current by introducing the speed or velocity at which the charges are moving and the number of charges. We're also able to redefine the volume current density J using the essentially some sort of density times velocity. So is there another way we can represent J? We've defined it in two different ways. Now let's figure out if there's another way to do it. So one thing we haven't really looked at is whether we can relate the current density to something from electrostatics. So thinking about moving charges, why do charges move? Charges move because of an applied electric field. So now we want to see if we can relate J to the electric field. So the velocity u of moving charges depends on the applied electric field E. This means that J is proportional to E, and we write that as J is equal to sigma E. So this is the third and final way of representing the volume current density. So it makes sense that sigma is a proportionality constant, and that sigma is equal to conductivity. So sigma is known as the conductivity of the material, and it's going to be in units of Siemens S over M, or mho over M. So that symbol, which is an upside down omega, simply means the reciprocal of ohms. So this particular symbol is called mho, because if you spell it backwards, it's ohm. So that covers volume current density. It would be good to know the different ways of representing the volume current density J, just so that you can take advantage of these different forms and apply them to various different problems.